This is 5.2 volume by slicing disc and washer. This will be the first of three videos that I've created for the winter break that will deal with three different methods for calculating volume using integrals. The first one that we're going to deal with is computing the volume of a rotational solid using the method of disks. In this video, we'll go through some notes and I'll answer examples 6 and 7 from the note packet from the 5.2 note packet. So let's get started. So the method of disks. When a region in the plane is revolved about a line, the resulting solid is a solid of revolution. So you'll see those words used a lot on the AP exam. They'll say solid of revolution. And then the line that it's rotated around is called an axis of revolution. And so the simplest such solid that we can think of is a right circular cylinder or a disk, which is formed by revolving a rectangle around an axis adjacent to one of the sides of the rectangle. So let's take a look at a visual representation. Here I have my yellow rectangle with a length of big R and a width of W. And then a thing you should note is that the rectangle itself is touching the axis of revolution right here. And then the long side, the R side, is going to be perpendicular to the axis of revolution. And that way that the width will always be parallel with the axis of revolution. This is really important because another method that we're going to discuss is going to take that role and flip it. So if I take this rectangle and I spin it around my axis of revolution, what I should end up getting is a disc or a cylinder that looks something like this. Okay? And then if we wanted to compute the volume of that disc, well then we would take the area of the top disc, which is actually just a circle, and we multiply it times the width of the disk, which we know is just W. And so we know that the area of any circle is going to be pi times big R squared, since big R represents the radius, and if we jump down to this diagram, I know that big R represents the radius of the circle, and then times the height of the disk, which is actually going to be a width of W. And so R is the radius and W is the width. To see how the volume, or how we use volume of a disk to find the volume of any general solid of revolution, we consider the solid of revolution by revolving that around the indicated axis. So we take this and we spin it and we get this disk. And then to determine the volume of this solid, we considered a representative rectangle in the plane region. And then when this rectangle is revolved about the axis of revolution, it generates a representative disk. So the volume is what we've already talked about, which is pi r squared, and delta x, which is actually going to be the width. This is our W. So now we've started putting it in terms of things that we're used to seeing. So delta x representing the width of any rectangle. And we're going to start how we always start, just by approximating. So approximating the volume of the solid by n of those disks with width delta x and a radius r produces the following approximation. It is also really, really important to note that the radius is usually not constant, and that's usually going to be where the rectangle touches the curve. So we know that the curve changes height, and so instead of r just being an r by itself, we rate it as a function, which is r of x sub I. And so the volume of the solid becomes the sum from I equals 1 to n of pi times this radius squared times delta x, which is my width. So this is my radius. This is the radius of the circle. And this is my W. This is the width. And since pi is just a constant, we're allowed to pull it out of the entire sum. And so it really is just pi times the sum of r times, or r of x sub I squared times delta x, which we know when we take this summation, we're allowed to rewrite it as an integral. And so I know that the volume of a solid, if we think about it this way, and we start with this representative rectangle, and when we rotate it, we get a disk like this, and this actually is going to look like what the whole solid looks like of this particular curve. So if I take this particular curve and I rotate it about this axis, it's going to make this kind of shape here. And then this rectangle will turn into this disk. And if I add more disks, I would end up getting something like this. And then, as we know with Riemann sums in a really general case, that as we let n go to infinity, as we increase the number of rectangles, they become infinitely more thin, and they actually approximate the curve better. And so we write the limit as n goes to infinity of pi times the sum that we've dealt with, and we know that we can take this sum and we can write it as an integral. So it's actually pi times the integral from a to b of this radius function, which we'll deal with in a second, squared dx. So let's try an example with it. Oh, sorry. So now we have the disk method. So there's two different methods that we can use, or there's two different ways to represent the disk method. So to find the volume of a solid of revolution, the disk method, we're going to use one of the formulas below. So we have a horizontal axis of revolution or a vertical axis of revolution. This works very similar like when we're finding the areas between curves, so we could use horizontal or vertical rectangles. It's really important that if we're going to use a horizontal or have a vertical axis of revolution, that means that we're going to have a horizontal rectangle. And when we have a horizontal rectangle, we need to solve for x and then change our limits of integration. But you'll see that in example 6c. Okay, so we have to solve for x and then we have to change our limits of integration. But we'll have a horizontal rectangle, and again, if this is our axis of revolution, this still follows our rule that the long side of our rectangle needs to be perpendicular with the axis of revolution. It also needs to be touching to use the disk method. Okay, so let's take a look at example 6. It's going to start off with a trig function. So find the volume of the solid formed by revolving the region bounded by the graph f of x equals the square root of sine x, and the x-axis, which is from 0 to pi, about the x-axis. So I'm going to take this whole curve and I'm going to rotate it around the x-axis. And what I've done, and what you should always do, is you should always just draw a representative rectangle. And then when you draw this representative rectangle, you should try to do your best to sort of sketch what the disk would look like. And if I take this rectangle and I rotate it, it should look something like that. And then if I add an infinite number of rectangles, which thins them out and turns into my solid or my revolution or my solid, it'll turn into that, my solid of revolution. That's the word I'm looking for. And so what we can do is we can actually use our formula for volume of a solid of revolution, which I know now is going to be v equals pi times the integral. And I'm integrating from 0 to pi, so from here to here. So it's from 0 to pi. And it's going to be the radius, which the radius in this case is going to be this, the square root of sine x. So the square root of sine x, and that function gets squared dx. Well, if I start working with this, that means that I can cancel out the square roots. So you get pi times the integral from 0 to pi of sine x dx. And we know now that the antiderivative of sine x, and this is going to be pi times the antiderivative of sine x, which is negative cosine x. And that's going to be evaluated from 0 to pi, which is going to be pi times the negative cosine of pi minus the negative cosine of 0, which I know now is going to be pi times 1 plus 1, which is 2 pi. So the volume of this football-shaped object down here is going to have a volume of 2 pi cubic units. Let's try another one. Revolve the region under the curve y equals the square root of x on the interval from 0 to 4, so they're giving you the limits about the x-axis, and find the volume of the resulting solid of revolution. So if I wanted to, I could draw my representative rectangle. I always want to be able to draw it so that it's completely between two specific curves the entire time. If that doesn't ever happen, then you take your rectangle and you flip it. But this one will actually work really nicely if we start with a vertical. So we're gonna just sort of draw a rectangle, and I know that if I were to rotate it, it would come around here, and I would have a nice disk. So I know that my radius is going to be the square root of x, and I'm integrating from 0 to 4. Okay. Also notice that your limits of integration are on the same vertical axis for the disk method, or the same horizontal axis, the same axis of revolution. So I'm going to say that the volume of this solid is going to be pi times the integral from 0 to 4 of the square root of x squared dx, which is really pi times the integral from 0 to 4 of x dx, which if I take the antiderivative of x, I know it's going to be pi times the antiderivative of x, which is x squared over 2. And that's going to be evaluated from 0 to 4, which I know is, if a 0 is my bottom limit, I don't actually have to evaluate it. So this is going to be pi times 4 squared over 2, which is going to be 8 pi. Okay, the kind of solid that you get when you do these rotations with these kinds of curves or with parabolas, these are going to be our paraboloids. It's going to kind of look like a cup. Okay, let's take a look at one last one where we're not going to use a vertical rectangle. We're going to use a horizontal rectangle. So for 6c, find the volume of the solid resulting from the revolving the region bounded by the curves y equals 4 minus x squared and y equals 1 from x equals 0 to x equals radical 3 about the y-axis. So if I start with this and I draw a vertical rectangle, the first thing you should realize when you draw the vertical rectangle is that your vertical rectangle is not touching your axis of revolution, which is not what I want. Whenever you're using the disk method, you need to make sure that your rectangle is touching the axis of revolution always on the interval. So we're going to take this rectangle and we're going to flip it, and we're going to draw a horizontal rectangle. So going like that. And whenever I have a horizontal rectangle, I need to solve my equation for x, and then I need to change my limits of integration. So taking y equals 4 minus x squared, when I take it and solve it for x, it's going to turn into x equals the square root of 4 minus y. And if I look at my graph, I realize that I'm now, instead of integrating from 0 to rad 3, I'm going to integrate from 1 to 4. And it's actually going to be a much easier integral to do. We could do the integral with the vertical rectangle, but that's going to involve a method that we haven't learned yet. It's going to involve something called shells, which will be in the third video out of 3. So let's calculate this integral. So I still know that volume is pi times the integral, and now my new limits are from 1 to 4 of the square root of 4 minus y squared dy, which is equal to pi times the integral from 1 to 4 of 4 minus y dy, which is going to be pi times the antiderivative of 4 minus y, which is 4y minus y squared over 2 from 1 to 4. And if I plug in, it's going to be pi times, when I evaluate 4 into this, it'll be 16 minus 8. And when I evaluate 1 into this, it'll be subtracted 4 minus 1/2, which is going to give me pi times 8 minus 7/2, which is going to be 9 pi over 2. So this is my volume, 9 pi over 2. Okay. The one last thing that we have to deal with in terms of the disk method is that we have been rotating around an axis, a specific axis, so x-axis or y-axis, but we're not limited to revolving or rotating around those specific axes. What we can do is we can rotate around any line. And so find the volume of the solid formed by, of the region bounded by the graphs f of x equals 2 minus x squared, g of x equals 1, and we're going to rotate it actually around the line y equals 1. So if this is going to be my solid right here, or this is going to be my curve, this is the 2 minus x squared, and then this horizontal line represents y equals 1. And you should also notice that y equals 1 and the line y equals 1 that we're going to rotate around, they're the same thing. So when I draw my rectangle, it's still going to be touching that axis of revolution, so we can still use the disk method. So if this is my rectangle here, I need to calculate the length of the radius. And since I know that this is going to be the top part of it, which is f of x, which goes from here all the way to the bottom, and I know that the bottom of the rectangle is going to touch at 1, which is g of x, this length right here, r of x, can be found by taking f of x and subtracting g of x. So I know that r of x, in this case, is going to be 2 minus x squared minus 1. Okay, so I need to find the length of this rectangle. If I take these two curves or two lines and set them equal to each other, they would intersect from at -1 and +1, so those would become my limits of integration. And I can also just clean this up a little bit. So r of x is really just 1 minus x squared. And so that's all I need to figure out my volume. I know that my volume formula will be pi times the integral, and our limits were -1 and 1. So -1 to 1 of 1 minus x squared dx. Squaring out this, it's going to be pi times the integral from -1 to 1 of 1 minus 2x squared plus x to the 4th dx. All I did was square out the inside here. And so I can take the antiderivative of that. So it'll be pi times the whole thing, the antiderivative of this inside, which will be x minus 2x cubed over 3 plus x to the 5th over 5. And we're going to evaluate that from -1 to 1. For the sake of time and saving space on the screen, when you plug in 1 into the function and plug in -1 into the function and subtract them and multiply it times pi, you should get 16 pi over 15 as the volume. So the volume of this solid, which is what we got by rotating this curve over the line y equals 1, has a volume of 16 pi over 15. That pretty much sums up everything that we can do with the disk method. Please reference the email for some practice problems that you can do that I will check when we get back on Monday.